Applications.
Hello.
Chintu sir?
Yeah.
Sir,
Hello.
now you may.
Yeah, audible?
Yes, yes, sir, you may start now.
Okay. So thank you, Devlina, for your introduction. At first, I'd like to say thanks to the organizer for inviting me and giving me the opportunity to present my work in this webinar. And thanks also the my senior Professor Utpal Sorkar uh, um, to invite me. And though there is some sorry for this technical problem, but okay, somehow we'll manage. Okay, so the title of my talk is Raman Spectroscopy and its application. So in my talk, what I will do, I will show you how we can use the Raman spectroscopy to study different uh, properties, different interesting properties of condensed matter system using under different external influences by Raman spectroscopy. So before going to start my this actual talk, I would like to uh, give some brief introduction about our institute. So can you go next slide? Yeah. So I'm from Bose Institute. This is 100 more than 100 years old institute, and it was established by the great scientist Acharya Jagadish Chandra Bose in 30th November 1970. So this is the picture shows that this is our main campus, which is situated at APC Road, Kolkata. It is just next building of Rajabaja Science College. Then we have other campuses in Kolkata and Kolkata and surrounding Kolkata. Like, can you go next slide? Yeah. So this is another campus, is Centenary campus, and also we have the campus at Darjeeling. Then we have some experimental farm at Muddamgram, then Falta. Okay, go next. Yeah, so this is the recent campus, which is actually Unified Academic Campus, which is situated at this Sector 5, Kolkata. And all the campuses of both institute will move to this new campus. This is a huge campus, and in the short time we'll shift there, and this will be the Unified Academic Campus of both institute. So now I'm coming to my talk. So we know that this noble electronic properties of material that depends on charge, orbital lattice, and spin degrees of freedom. So we can tune the properties of this material by tuning this degrees of freedom. So how we can tune this properties? So one is that next. Yeah, dimension, the dimension is an important parameter. If by changing the dimension, we can change the material property. Then you can also have some external control like next. Yeah, like temperature, pressure, electric or magnetic field, photon, and chemical doping, etc., are the external parameter by which we can control the electronic properties of materials. So for application of this material, so tuning and the understanding of this property is very essential for their future application. So my research aim is that okay, using the spectroscopic technique like mostly this Raman spectroscopy to study the different material, low dimensional material that can be one zero dimension, one dimension, or two dimensional material using and under external influences like, as I said before, temperature, pressure, magnetic field, electric field, to study their response. Okay, so next. So next, yeah. So as we use, no, yeah. As we'll use the spectroscopic technique, we know that spectroscopic technique, in a we need a in electromagnetic radiation, and that radiation, how we define a radiation? A radiation is energy that propagates through free space or through the medium in the form of a electromagnetic wave. So we know the in electromagnetic radiation there are two components. Uh, Actually, I thought that most of the lot of students will be there, so that's why I made this presentation little bit for the student. Okay, so this, hello, yeah, can you mute
Please,
the,
please, please, other participant, mute your audio.
yeah, can you mute the other?
I have
Okay.
muted, sir, but
Okay, so we know that electromagnetic field has electromagnetic radiation has two components. One is electric field and other is magnetic field. Now we characterize the electromagnetic radiation using this wavelength or frequency, amplitude, and velocity. Now, when this electromagnetic radiation interact with a molecule, then what will happen? That radiation will be some part of the radiation will be scattered, and some energy from the incident radiation molecule will absorb some energy from the incident radiation during the scattering. So what happened then? After absorption of the energy, so there will be some excitation. What kind of excitation we can see? So that can be a electronic excitation, then rotational excitation, vibrational excitation, spin excitation, those we'll see. Okay, so since I am interested about this only the vibration, so I will mostly focus on the vibrational excitation. And if you go in the next slide, next, can you go next? Okay, so from the energy diagram, we can see that we can get an idea how much is the electronic energy gap, then vibrational energy gap, rotation. The electronic energy excitation occur between the two electronic state, and which is much higher than the vibrational energy, which is in the infrared. The on the electronic excitation occur in the optical range, then the vibrational energy, which is much lower than the electronic excitation energy, which is in the infrared range, and then the rotational energy, which is much lower than the vibrational energy, which is in the microwave range. So in a spectroscopic technique, so as I said before that we need some excitation, electromagnetic radiation to excite the system, to probe the system, to probe the electronic energy, to probe the vibrational energy, to probe the rotational energy. We need different kind of electromagnetic radiation. Can you go next? Okay, so you know that this is the whole range of our electromagnetic radiation. It start from radio frequency to the to the gamma ray. Then go next, yeah. So if you look that for in the radio frequency range, we use nuclear magnetic resonance, yeah, NMR, ESR technique we use to get the spin energy, nuclear spin or electronic spin. Then for vibrational energy, we use mostly the IR spectroscopy and Raman spectroscopy, and it is in the infrared region, and in the for to measure the optical excitation. The technique we use is optical absorption, photoluminescence, fluorescence, phosphorescence, those things. And this the energy range is in the visible range. Okay, so now I will concentrate on the Raman spectroscopic part. Go. Okay, so Raman effect. Raman effect is the inelastic scattering of light by matter when a monochromatic light is incident on a molecule or in a medium. Then we can see that in the scattered light, instead of instead of incident the frequency, the energy of the incident light, it, there will be some radiation which is energy higher or lower than the incident radiation. The change of the radiation in the scattering side is called is due to the interaction of light with the this vibration due to the vibration of the molecule, and this is called the Raman shift. This shift is called the Raman shift, and the effect is called the Raman effect. And Raman got a Nobel Prize for this great discovery in 1930. Okay, so next. Yeah, so this is the small note actually published in 1928 by C.V. Raman. This is the almost half page note. It is the summary of 6 to 7 years of his experimental data, and and this is the actually the report is on Raman effect, and he got Nobel Prize just 2 years after this, and the published of the paper in Nature in 1928. Okay, next. Next. Hello. Yeah. So how we can explain the classically the Raman effect? Raman effect, we know that the electromagnetic radiation we can write is EI is equal to E0 cos of twice by nu t. Nu is the incident frequency of the incident radiation. Then we know that when a radiation, some molecule or from some molecule you place in a electromagnetic radiation, then the positive part of the atom or molecule will move towards the negative side of the field, and the negative part of the molecule or atoms will go towards the positive side of the field. So there will be some polarization, and that will induce some dipole moment. So that is P is equal to alpha into E. This alpha is the polarizability, and we can, due to this polarization, there will be some displacement, and due to the displacement we can write is Q is equal to Q0 twice by nu t. And if we go, then finally we will get the next slide. Finally, we get the final expression. We can see that there are three terms. First term is that the frequency of the, you can see the frequency of the frequency is the same as the incident frequency, and in the second and third term we can see the frequency is greater or lower than the incident frequency. Thus the first term gives the Rayleigh scattering. This is elastic scattering of light, and the second and third term will give you the inelastic scattering. That is, one is Stokes, where the frequency is decreasing, and another is anti-Stokes frequency is increasing. Okay, go next. Yeah. So quantum mechanically, if you see that when there is an energy diagram, so now when the light is incident on it, then after absorption of light, the system will go from the ground state to the to some virtual state, and from the virtual state, if it goes back to the ground state, then you can see that this scattering will give you the Rayleigh scattering. And if the system goes from the ground state to the final state is the some vibrational excited state, then you will get the Stokes line. And if you go if you already system in the excited state, then it goes to the final state is the vibrational ground state, then you will get the anti-Stokes line. So when the Raman scattering occurs, elastic, that is Rayleigh scattering, Stokes, anti-Stokes, all will is occurring in same time. Okay. Okay, so go next. Okay, now I'll come to the solid system. We know that lattice, when some due to the some external perturbation, lattice vibrate, and in a monoatomic, a diatomic lattice, we can see that there are two types of vibration. One is acoustic mode, another is optical mode. In the acoustic mode, the atoms this vibrate in the same direction, so this overall this center of mass moves, and in the optical vibrate mode, these atoms are vibrate in opposite direction, and the center of mass remain unchanged. And those gives this phonon. You know, the phonon is the quanta of vibration, and if you look the phonon dispersion curve, let's say for example here I have given this gallium arsenide is a semiconductor, and if you look the phonon dispersion curve at the gamma point, that is this k is equal to 0, we can see there at k is equal to, in the acoustic phonon mode, is goes to 0 at k is equal to 0, but optical phonon modes, they have some a finite value at k is equal to 0. And apart from this optical and acoustic mode, you have also the surface optical phonon mode that appears due to the at the interface between the two dielectric medium. And this surface optical phonon mode decays very rapidly. That's why only in the we can measure the surface optical phonon mode in the nanostructure material, means the low dimensional system. So can you go next? No. Yeah. Okay, so in the bulk system, we know the phonon from the conservation of phonon momentum, and then we can see the Raman this Raman scattering occur at k is equal to 0. So we get the for bulk system, we get the phonon frequency which is at k is equal to 0. So we get the optical phonon mode. But next, in the low dimensional system, we can see that this k is equal to 0 selection rule is relaxed, and the phonon which is in the first below in the below, so all the phonons can participate in this scattering, and that will give you the change of the Raman line shape. If the phonon frequency, the phonon dispersion curves goes means downwards, with the increase of k, then we can see see a asymmetry in the phonon spectrum in the lower energy side, lower energy side of the spectrum. And if you the phonon spectrum goes up with dispersion camp goes up with the value of k, then we will get a asymmetry in the Raman spectra in the higher energy side, as you can see from the picture in the right side. Okay, go. So now I'll come and then confinement effect, phonon and confinement effect. We know in the low dimensional system, electrons confined, and that we get some change of optical property. Like electron, phonon also confined in low dimensional system. So due to the confinement effect, how this Raman spectrum will be? That was next. Uh, Go next. Yeah, that was given by this Campbell and Fawcett model. From this model, you can calculate the intensity of Raman intense in Raman mode, which is given by this equation, this top equation. Then the where omega is the frequency, and the omega q is the phonon. Yeah, this is the dispersion curve, represent the dispersion curve, and the zero q, that is represent the weighting function, which is expressed as which is a function of diameter of the diameter or size of the particle. So from this intensity, you can see that the intensity of Raman mode or gives the is a function of the this diameter, and that will also change the shape of the system. So from this model you can calculate the particle size. You can estimate from the particle size from the Raman spectrum. So go next. So you can see here is the calculated Raman line of a silicon nanocrystal, and the solid line is the for silicon bulk, and you can see the Raman spectrum is a symmetrical Raman peak, and as we decrease the size due to the confinement effect, we can see some asymmetry in the lower energy side, and you can see this how is the asymmetry is increasing with the as we decrease the size, as we decrease. So from this calculation and experimental data, you can get an idea, you can get the size of the particle from the Raman measurement. So go next. So here is the next. Yeah, here is the example of a germanium nanowire of different size. You can see the Raman spectrum, which is in the right side of the slide. You can see that particle size is decreasing. Upper one is the small particle size, and lower one is the biggest particle size. Oh, you can see that when the particle size is big, is more symmetric, and as we decrease the particle size, this asymmetry is appearing. And from where we have estimated the particle size, which is from the 5 to 10, and we estimated, and also it is consistent with the TEM analysis of the sample. Okay, go next. Now, as I said before, that I will show you that effect of such. And so first I showed you that the effect of the size. Now I will show you the other external influences like the doping, the photo doping. How we can dope by photon. So we know in a semiconductor, if you irradiate the semiconductor with light or laser light with a appropriate energy, then the electron and hole will create. And if you somehow they can separate them, the electron and hole, then you can tune the charge concentration of the in the semiconductor. So how this charge, if you can change the charge concentration within the system, then how you can measure this, how we can the effect of this charge in a Raman spectroscopy. So go next. uh, Actually, when you have some charge in the system, then that charge, the field of this plasma, that will create a plasmon, and that field of the plasmon and the phonon vibration also give you the some dipolar effect, and this dipolar electric field and the plasmon electric field interact, and they will create some coupled plasmon phonon mode. So we can get the plasmon phonon mode by changing the charge concentration within the system, and that we can measure from the Raman spectroscopy. Then in the next slide, I will show you various on very nice experiment that we have done in a few years back. So go next. So next, sorry. Next. Yeah. Okay. So you can see here that we use indium arsenide nanowire. That nanowire, indium arsenide nanowire, we can see that this and we focus the laser light using a microscopic objective, and you can see in the top figure actually the indium arsenide nanowire on the substrate, and we focus the laser light on the substrate. So this is we did the experiment in the air, and when the laser power is very high, then we can see the hello. Hello. So there will be two different effect. One is the due to the photoelectric effect that will create some electron and hole. Then in the second case, due to the strong localized electric laser light, there will be some local heating. That local heating, since the experiment we have done in the air, so that local heating will create some oxidation on the surface of the nanowire. That oxide layer, and that oxide layer will act as a charge trap for the whole trap. So then we can see that sorry, this will be act as a electron trap. So electron will be trapped. You can see in the right side picture, so electrons will be trapped on the oxide surface, and we can get that will create an built-in electric field, and that will finally the in the core semiconductor, indium arsenide core semiconductor, will get some increase of electron. So by using the photon, we can tune the charge concentration within this material, and that we have measured. So next, yeah, that if you look in the Raman spectra in the no, previous. Hello, go 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 previous slide. Go back. Yeah. Okay, so if you look the Raman spectrum, then we can see that generally in the normal Raman spectrum, India Raman spectra, spectra give the TO and LO mode, and with some SO mode, surface optical phonon mode. But if you look in the right side, top right side spectra, we can see that as we increase the laser power, we there is some new peaks appear that is shaded by this brown color. So that new peak is due to the plasmon phonon couple mode. So and the position of the plasmon phonon couple mode depends on the charge concentration, and that we can control, that we can increase by the increase of laser power. And we can in the next slide go. Hello, go next. Next. Yeah, from analysis we can get the peak position. We can get the charge concentration with the laser power within the whole concentration, actually whole concentration within the nanowire by laser increasing laser power. Next. And this is the actually in the right side, yeah, in the bottom you can see some spectrum. Those spectrum we have measured using different using the same experiment we did, but in the vacuum. But you can see as there is no oxygen, and so oxidation is not occurring in the surface, and that's why electrons are not trapped by the surface of the surface of the nanowire, and we can see there is no appearing, there is no presence of the CPLP, means the coupled plasmon phonon mode. So in this experiment, what we did that we can tune the charge concentration within the nanowire, and by Raman spectroscopy we can monitor this charge concentration from the CPLP mode. Okay, next. Now I'll come to the effect of pressure. So you know that when you apply the pressure, then the lattice constant of a system will change, and that will change the volume. So go next. Yeah, that will change the volume, and you'll reach some, maybe the new structure or new phase of the system, or it will modify the electronic configuration of the system. And there is a parameter which is called Grunetian parameter that describes how the volume change, the vibrational when the volume will change, then how the vibrational property will change. That is defined as del ln omega I by del n v. Ln v, omega is the frequency, and so using the pressure you can change the structure of the system. You can get the new phase, or you can get the electronic configuration. So here I'll show you in the next slide that again we did the India nanowire, the high pressure experiment. We use it is a diamond anvil cell, DAC cell, and we place the nanowire at the, you can see in the right side picture that nanowire is at the gap between the two diamond. They are actually, the tip of the diamonds are opposite to each other, and they are facing to each other, and if you apply little force in the between the diamond, then as the pressure depends on the area, there some huge pressure will create within the sample. So by this this experiment we can apply the pressure of this in the system up to 60 GPa. Okay, go next. And we can see that as I said before, that if you apply pressure, then new structural transformation will occur. Okay, so if you see that this color plot, there's initial Raman mode, this is LO and TO mode. After some pressure, it vanishes, and new modes are appear. So these new modes are the indication of the signature of the new phase of the system. Now, okay, this structural property, we know that it will change, but I want to show you in this work that that how using Raman spectroscopy, how we will get the electronic change of electronic band structure within the system. So the as we apply the pressure, then the band gap will change, band gap will increase. Now if you do the Raman spectroscopy with a fixed laser line and apply the pressure, then that pressure will tune the band gap, and as the laser line is fixed, so you will get sometime the gap of the system, band gap of the system is close to the laser frequency. So there you can see some resonant Raman behavior. So you will see some intensity enhancement. And if you go to the next slide, go next slide. Okay, so there you can see in the left side, you can see the intensity of the different Raman mode as a function of pressure. Then there we can see that there is some resonant enhancement of the peak. Those enhancement is due to the resonance of this energy of incident laser energy with the band gap of the system. So by this way, you can get the information band structural information, or information of band structure from the Raman measurement. So okay, so this is the effect of the pressure, and using Raman study you can get the structural information as well as the electronic band structure, information of electromagnetic structure. Go next. Okay, so now the temperature, as you know that the pressure is an important thermodynamic parameter. Similar, the temperature also an important thermodynamic parameter to which change the how we change the system. Okay, go next. Yeah. So you know the phonon number of phonon which is given by this distribution function in the right side of the top corner. You can get there, and you can see that as the number of phonon depends in the different level depends on the temperature. So we get that the intensity of Stokes is from the ground state to the vibrational excited state, and anti-Stokes is vibrational excited state to ground state. So the intensity of Stokes and anti-Stokes has some dependence on the temperature. So you can get the intensity ratio of Stokes and anti-Stokes from this as I mentioned in the slide. Okay, so now by changing the temperature from the by measuring the Stokes and anti-Stokes intensity and getting from their ratio, you can get the information of the temperature of the system, lattice temperature of the system. Now go next. Okay, this is the from intensity change, and also the energy. So you know when you change the when you increase the temperature, then there will be some interaction, that is phonon interaction. So one phonon energy phonon will interact with the other and create some lower energy phonon, so that will give some the energy shift. Similarly, thermal expansion, if you increase the temperature, there will be some thermal expansion. Thermal expansion will also increase the lattice constant. So by so now the effect is phonon interaction and thermal expansion together will give you some change of energy. So that means the Raman frequency and the phonon frequency of the system will change. Now you can measure the Stokes anti-Stokes ratio or the frequency change to frequency, Raman frequency, the phonon frequency from the Raman measurement. That will give you that will be like a thermometer which will give you the temperature of the system. So you can use the Raman spectroscopy as a thermometer to study the temperature, to measure the temperature of the system. So go next. So using this behavior, so we did a very interesting experiment, that is you can see in the picture that nanowire which is suspended on an between the two, like a bridge between two pads. So it is suspended. Now if we focus the laser light at the middle in between, then what will happen, that laser will create some heat, that will give you some local heating. Now the local heating, you can measure how much temperature is there, you can measure from the Raman spectrum, because Raman spectrum will give you the information about the temperature. Now the how much temperature will increase in the middle of the nanowire, that will depend, on the thermal conductivity, thermal property of the material. The material means thermal property of this nanowire. So from the heating in from the local heating, that we can measure from the Raman spectrum or phonon frequency, that give you the information about the thermal conductivity of the material. So this is very simple experiment, but you can get the thermal property, thermal conductivity of the material from the very simple measurement. So now go next. So we used two types of nanowire. One is you can see in the same picture. One is defect free. This is very clean and clean sample. Another is defective sample. And we want to compare their thermal conductivity using the same method. And we have found that the this defective nanowire is the thermal conductivity of the defective nanowire is 10% lower than the defect free nanowire, because the defect side give some extra scattering that will restrict the thermal properties of this material. So using a very simple experiment, you can get the thermal properties of the material. Go next. So recently we have did another experiment, that is there the nanowire. This is germanium nanowire again, that is grown like a suspended nanowire. It is suspended from the substrate, and we focused. We did the same measurement as I said before, but at different point of the nanowire. So that will give you the length. That will change the length of the nanowire, and we measure the thermal conductivity of the nanowire, and that measurement data is very much consistent with the, is very good matching with the other measurement other data which is measured from very sophisticated technique. And we did the diameter variation, length variation, and got the very nice result, and we published just recently in the Physical Review Applied. Okay, go next. Yeah, you can see that the temperature, that this delta T is Q RT plus LQ by AK. This is the thermal conductivity, and we know all the parameters. That is, Qt is the how much flux equivalent temperature depending on the laser power, and L is the length, and and A is the area, cross sectional area of the nanowire. And from this Raman measurement, we got this thermal conductivity, and also we did the temperature dependent thermal conductivity in this using this measurement. Okay, go next. Now so I come to the chemical doping part. So if you know that when we do some chemical doping, that means you incorporate some other material within the lattice of the host material, so that will create some the defect within the system, also create some the strain within the system. So that strain, the strain will change the lattice constant, and immediately you will see the phonon frequency will change, and that you can measure from the Raman spectroscopy. Go next. So here's the example. Yeah, an example of this germanium doped with tin, and we can see that actually this idea of this work is that we know that the germanium is an indirect band gap semiconductor, and if you can if you can change the indirect semiconductor to a direct band gap semiconductor, that will create that will be means great achievement, because the application photonic application of direct band gap germanium is huge. So it was the motivation of this work to get the direct band gap germanium nanowire by tin doping. So left side is the doped picture of the EDAX mapping of the germanium, tin doped germanium nanowire, and you can see in the right side the Raman spectrum and of this tin doped germanium, and we can see the how the peak position is changing, and from this change of peak position we can estimate the percentage of tin present in the system, and also this you can get the other the vibrational mode present in this nanowire. And finally we did some finally we did some optical measurement, that is photoluminescence, and which go next. Yeah, where you can see that this germanium is behaving behave like direct band gap, and that paper has been published yeah, in Nature Communication. Go next. Okay, so now I'll show you the electric field, effect of electric field. If you let's say you have a sample and you have two electrode between the two electrode, then if you apply the electric field, so if this material is a piezoelectric material, then what will happen? This there will be some piezoelectric effect, and that will change the length or width of the material, and that will create some strain within the system. So in that was the idea for this experiment, that if you apply the electric field of a material to check the material is piezoelectric or not, and then we did the measurement. uh, Go next. Yeah, so this is the device. You can see the we use my MOSC2. This is the very well known, I think, and this is TMD's group, very well studied material in TMD's group. And we use the MOS2 plate in between the two electrode, that is gallium and the reduced graphene oxide is the two electrode. Then we apply the electric field, as you see in the right side picture, you can see. So this electric field, that is due to the piezoelectric effect, so you can see some strain along the z direction in the perpendicular to the xy plane, and we can see that this due to the strain. So we see the Raman mode, if the increase of electric field, as the Raman mode is changing. Go next. This is the result. Yeah, the result of the Raman mode, we can see as we increase the laser, the electric field, the mode is changing from the original position to the lower frequency. So from the shift, we can measure the how much strain is there. So now means to confirm that this is due to the strain effect, we did the measurement in the by changing the polarity, means that just we reverse the electric field, reverse the field direction, and we can see that. Go next. Yeah, if you reverse the electric field, then what will happen? The strain will be in the opposite direction, and since the material is on the top of the substrate, though, so the strain effect in the opposite direction is lower than the strain effect in the previous direction. And as a result, we can see that the shift in this configuration, the shift is very lower than the other direction. And you can see that in the right side, the delta omega change from positive and negative direction of the electric field. So with this experiment, I want to give you the message that we can measure the piezoelectric properties of this material by using Raman spectroscopy, and this paper recently has been published in NPJ 2D material and applications. Okay, go next. Okay, so another aspect of this Raman spectroscopy, that is to check the symmetry of it. So if you just grow a sample and you want to check the, okay, this sample is good, means the crystal property, if it is single crystal, then you can check the symmetry of the system. So to check the symmetry of the system, you can do the polarization dependent Raman study. So go next. Okay, in the polarization dependent Raman study, what we can see, the intensity of Raman effect, Raman intensity can be calculated from this equation. You can see that there is a EI and ES. EI is the polarization of the incident radiation. ES is the polarization of the scatter radiation. Then RE is the Raman tensor. Okay, so from this Raman tensor, if you know this Raman tensor of the system, then you can calculate the intensity of the modes, and that intensity now you measure this polarization dependent Raman measurement you can perform, and you can match with the intensity profile what you have calculated. From there you can verify the symmetry. You can you can verify the symmetry of the system. Go next. So here is the example of this Jadar SIS crystal, that is actually a topological material, semi-metal, topological semi-metal material. And you can see the polar the right side and the bottom figure. You can see that the different mode shows the different symmetrical behavior. And the measured intensity, there's a scatter point. Raman measured intensity of this mode, scatter point, is very consistent with the calculated result. So in this way you can check the symmetry of the system. Next. Next. Okay, so as I said before that, the lot of things you can measure from the Raman spectroscopy. Those are the phonon, mostly phonon related thing. But here I want to mention also you can directly measure the elastic, in the electronic. Hello. Hello, can you stop? Yeah. So directly measure the electronic excitation state from this inelastic. That is called inelastic. Mean the Raman spectroscopy. Just I would like to. I will not go detail about this, but I would like to mention the how. So next. Okay, go next quickly. Yeah, so you can diagram, you can see this is not a phonon energy diagram, this is electronic energy diagram. So from the vibrational ground state, electron will go to the excited state, and from ground state, from there electron whole electron will come to the recombine to the valence band, and you can measure the excitation, electronic excitation energy using the electronic Raman scattering. So go next. Little bit first. Yeah. So you can measure the charge and spin excitation of material using the Raman spectroscopy. Actually, go next. Next. How you can see from this? If you see the look carefully, then you can see the how the excitation will occur. In the charge excitation, there will be no change of spin, and for spin excitation, you will get the change of spin. Go next. 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 Yeah, you can see the charge excitation change of delta spin, that will be delta. Actually, delta is equal to 0, and spin excitation, that is delta, is equal to plus minus 1. So using this technique, this is very go next. This is my very old work. It is published in the science. This is actually artificial lattice, and where it behaves like a simulator, quantum simulator, and where we create we have created that the lattice, hexagonal lattice, and that lattice, due to the interaction between the lattice, creates some electronic state, and under the magnetic field we measure the behavior of how the electron state is changing. So this is the first quantum simulator we realized in the semiconductor uh, material. So I'll not. This is very means long work, so I'll not go details about this. But what I want to mention here, that using the Raman spectroscopy, this inelastic scattering, you can also measure directly the electronic excitation state, electronic correlated state, using this technique. So go next. How much time I have? Hello. So
So
just I
you
want.
5 minutes or like.
Okay, so just quickly, I want to mention this thing. For this is the some kind of chemical or chemistry or biology for chemistry and biology people. Actually, whatever I have discussed before, that was the solid system, and we talked about the phonon and the electronic excitation. Now, Raman spectroscopy. This is a very powerful technique, but since it gives the vibrational fingerprint of the molecule, then why, I mean, what is the application of the Raman spectroscopy in biology or medical sciences? Actually, that I have not mentioned before, that Raman spectroscopy is a very powerful technique, but the scattering cross section of this technique of this scattering is very small. You can imagine that one photon will come as a Raman photon if 10 to the power 7 number of photon incident on 8. Okay, so you can imagine that it's very weak scattering process. So that's why after the discovery of Raman effect, so long time it has not been used by the biologist and chemist or chemist, because the very weak scattering, the weak signal. Then go next. Yeah, in 1974, there was a breakthrough. Actually, this scientist, policeman, they observed that if the molecule adsorb on silver, they did some experiment on the silver electrode, and they did the experiment on pyridine. The pyridine molecule adsorb on the silver electron, and they showed some strong enhancement of Raman signal. Initially, they thought that this is due to the rough surface of the electrode, because in the rough surface we know the area is large and more number of molecules are adsorbed on the surface. But after 3 years, go next. So you can see the these two group independently, they found that this enhancement is not due to the surface. This huge enhancement. Huge enhancement means that it is of the order of 10 to the power 11 to 15 order of enhancement, is not due to the only the surface area increase. So this is actually, they told that this enhancement is due to the two effect. One is the electromagnetic effect, another is the chemical effect. So go next. Next. Yeah. Just a chemical electromagnetic effect is the long range effect, and the major component, major enhancement is due to the electromagnetic effect, and due to the localized electromagnetic field on the metal surface. And the another is the chemical effect. Chemical effect is due to the charge transfer between the molecule with the metal surface. So one enhancement is due to the localized electromagnetic field on the surface of metal particle, and another is the charge transfer. This is chemical effect due to the between metal and the molecule. So, but the major component means the most of them is 10 to the power 9 to 10. This order of enhancement is occurred due to the this electromagnetic part, and the chemical enhancement is like 10 to the 2 to 3, this order. So go next. So this enhancement, what is the reason behind the this electromagnetic, huge electromagnetic enhancement? So we know that plasmon means the metal nanoparticle, this coherent the oscillation due to the interaction with the electromagnetic field. So that is called plasmon, and that plasmon, due to the interaction of this plasmon with the electromagnetic field, that localize some electric field on the surface, and that localized electric field will excite the molecule adsorb on the surface. So that will enhance the Raman signal. Go next. So you can see that here is the schematic representation of a measurement. So you have some number of molecule, let's say N, and I is the incident laser intensity of the incident light, and then I NR is the scatter light. Now the intensity of the scatter Raman light, Raman scatter light is proportional to the number of molecule and the proportional to the intensity of the incident light and the scattering cross section of the molecule. Those are the parameters. But if you go next, if you add some metal nanoparticles, since the nanoparticles are large surface area with this molecule, then if the molecule adsorb on the surface of the metal nanoparticle, then what will happen? So instead of, you can see now the intensity, that you can see that some extra term in the intensity, which is the EMGSR RB. This is the electromagnetic enhancement term, and that electromagnetic enhancement term is due to the localized electromagnetic field by the nanoparticle. And if you go next, and this magnitude of this enhancement factor, which is of the order of 10 to the power, this 4, means E initially before the nanoparticle if it is E1, and after nanoparticle if it is EL localized, then the enhancement, total enhancement will be EL by EI to the power 4 order. Okay, so that means if your molecule is adsorbed on the surface of a metal, mostly actually the search enhancement occur by this metal is gold and silver. Those metals are very efficient for the, because this localized electric field depends on the dielectric properties of the material, so mm, and then if the molecule adsorb on the surface of this metal nanoparticle, so you can get the strong signal from the molecule. Even you can measure the Raman signal from a single molecule also. So that is the beauty of this technique. And after that, the biologist and chemist are means application of this Raman spectroscopy in biological sciences, medical sciences, then chemical science is hugely enhanced. Okay, go next. So these are the some simulation result how this enhancement or means electromagnetic field localized on the surface. This is the COMSOL simulation, and you can see if there is this, if there is a single particle, this again the strong red part is the localized electric field, and right side the graph shows the enhancement factor for a single particle. You can see the enhancement factor is of the order of 10 to the 3. But if you make a dimer like that, go next, and dimer, then you can see this enhancement at the gap between the two nanoparticles. If it is very narrow gap, then there will be strong hotspot. This is called hotspot. And the enhancement, you can see how this enhancement the right side, the enhancement is of the order of 10 to the power 7. Go next. Yeah, and if you have a cluster of nanoparticle, then you will see that this is a collection of many dimer like part and thing, and you will see a lot of hotspot within the system. And if you add the molecule in this cluster, then if the molecule adsorb and the hotspot, then you will get a signal from the single molecule Raman signal. Okay, go next. Yeah, so this is the actually we published on this in this area. We published two papers. One is this DNA mediated wire-like cluster of silver nanoparticle. This is ultra sensitive substrate, and also another one is the this AU nanoparticle functionalized 3D MOS2 nanoflower and efficient search matrix for biomolecule sensing. Okay, so go little bit, just I want to mention. So in the first work, Next. Yeah, so we use DNA and we grow the nanoparticle on the surface of the DNA, and that DNA mediated this nanoparticle act as the substrate for the cells, and we absorb this methylene blue molecule for Raman measurement, and we can see that go next. Next, yeah, you can see the intensity of, we can measure the Raman intensity of this molecule, methylene blue molecule, up to the picomolar concentration. You can in the right side you can see the Raman. We can easily identify the Raman modes of this molecule up to picomolar concentration. Then go next. Next. Yeah, in this work, what we do, we use the MOS2 nanoflower, and we decorated the MOS2 nanoflower with gold nanoparticle, and that gold nanoparticle acts as the substrate and enhance the Raman signal, and we measure the Raman signal of this gold nanoparticle. Of the bilirubin. We use bilirubin as a pro molecule, and we can see the up to very low concentration we can measure the bilirubin molecule even in the presence of some in the this human serum, then dextrose, cholesterol, phosphate. Those are, we know that those components are present in our blood. So in the presence of those molecule, those chemical and those molecule, we can also measure the Raman modes of bilirubin up to very low concentration. So this is the this technique, the surface enhanced Raman scattering technique, is very useful for the biological and medical sciences. So go next. So now the conclusion is that just I want to conclude in this way that Raman spectroscopy is a versatile, convenient, non-destructive characteristics tool in the physics of in the field of physics, chemistry, and biology. So you can see that actually I tried to show you the how we can use the Raman spectroscopy in different area and with our some recent work. Okay, thank you. The next slide. Yeah, I would like to just acknowledge my students who did all the experiment, and then my collaborator, then national and international collaborator, and the funding agency CRB and Bose Institute. Thank you all.
Thank you, sir, for such a wonderful presentation. Um, Now the session is open for discussion.
Okay.
You may raise your hand or you may put it on the chat box. There are already some questions in the chat box. So should I read it for you, sir?
Okay.
It's a question from Neeraj Kumar Mishra.
Yeah.
He asks,
I am unmuting you. Hello, I am unmuting. Neeraj, you directly ask the question.
yes, it's better.
Hello, Neeraj. Hello, Neeraj. Are you listening?
Hello.
Hello.
Sir?
Hello.
Sir?
Yeah.
Hello.
Yeah. I hear you.
Am I audible, sir?
Yes.
Yes, sir. Sir, my question is that this Raman phenomena differs from second and difference frequency generation, or it is same? as in case of some frequency and a different frequency, we also get the output of light is greater than the frequency of the output frequency of light is greater than the frequency of incident light.
Yeah, okay. So, okay, there are two types of Raman scattering. One is Stokes scattering, and another is anti-Stokes scattering. When a photon incident on a let's say in a molecule, then if molecule is in the vibrational ground state, then after the incident of this electromagnetic radiation, that will create some vibration will be created. So that vibration by absorbing energy from the incident radiation. Okay, so in this way, when you will see the scatter light, that light will decrease, this energy of the light will decrease, because the some energy has been already absorbed by this molecule. Okay, so if this is the one type of shift, that is called the Stokes shift. Now, if the system is already in the vibrational excited state, then you just see that light is incident on a molecule, and then there's the vibration stop. Then what will happen, that the vibrational energy will be added to the with the incident radiation energy. And in that case, when you will see the scatter light, that energy will be higher than the incident light. But in both cases, the energy difference is the only the vibrational energy. So, and the second case, we call it is anti-Stokes light scattering. Okay,
Yeah.
that's why the energy for anti-Stokes energy will be more than the incident laser light, and Stokes energy will be less than the incident laser light.
Yeah. Okay.
Okay, so
But there is
yeah, still. If you have any other, I mean, if more questions, you can always write to me. No problem.
Sir, there is another question from Dinesh Mahato. So he is
Okay.
asking how to decide the laser wavelength for Raman spectroscopy.
Okay, so laser wavelength generally for the depending on the sample character. Actually, if the sample is not means don't have the any fluorescence background in the generally we use the laser light in the visible range during the for Raman measurement. But in the if the sample has some strong fluorescence in this region, then you have to change the laser light. Otherwise, the Raman is very weak process, and photoluminescence or fluorescence, they have a strong scattering cross section. So if you excite the system by some laser light, which is also giving the excite the electronic, give the electronic excitation like photoluminescence, then, in the strong background of photoluminescence, the laser Raman, you cannot measure, you cannot see the Raman line. So that's why, depending on the nature of the sample, you have to choose the Raman line. Otherwise, if it is no PL background, then you can just do the using any laser light. Okay, and but always you should remember that the scattering cross section is inversely proportional to lambda to the power 4. So if you use a laser which is longer wavelength, then the scattering probability will again decrease. Okay.
Sir, there is a question from our YouTube participant also, Murali Krishna Hari. He is asking that can light used in studying the novel coronavirus?
Yes. Okay. So Raman is a vibrational, gives the vibrational fingerprint of a molecule. And if we know that if we measure any virus or any molecule, and we can identify some marker peak for this particular molecule, then you can measure it. And definitely, I think there are some report that already people using Raman spectroscopy to measure the coronavirus. Okay.
Sir, there is another question
Uh,
from Soham from Presidency University. He's asking
yeah.
to know more about the vibrational energy levels. Which process
Yeah.
is most efficient? Also, will the enhancement factor EF
Which process? Yeah. Okay.
suffer from impurities in the sample? If yes, then how much deviation would be expected from pure sample?
First question, Shom, yeah. I like to know more about the vibration energy, which process is most effective.
Yes.
Okay, first answer question. Answer of the first question is that okay. So we can use the IR spectroscopy and we can use the Raman spectroscopy for the get the vibrational energy level. Okay, so both the technique will give the vibration energy, but they are not means they are complementary to each other. One, if the mode is allowed in the active in the IR spectroscopy, it will be inactive in the Raman spectroscopy. Also, and this is the point of view from the selection rule is different for Raman and IR. But also the experimental point of view, I want to say another. Difficulty in IR spectroscopy is that IR is very much sensitive to the water molecule. So when you do the experiment in the IR spectroscopy, that the water will give you strong background, and that will very strong background, very strong noise. Whereas in the Raman, we will not get such the water background will not affect any signal. So that's why experimentally you can say that Raman is more easier, and also the you don't need for sample preparation. You just put the sample on the under laser and you can get the Raman spectrum. Okay, so that's why it is easier in Raman than IR spectroscopy. Okay, and the
So, due
second
to limitation
question.
of time, we can take only one question. I can allow
Okay, so
Sukhvinder Singh.
maybe you can write to me.
Sukhvinder Singh, you may ask your question, please.
Hello,
Yeah,
hello, Sukhvinder.
yeah, yes,
Hello, Hannah.
Yes.
yeah, yes. Tell me.
How Raman spectra is different from PL spectra if we use the same excitation wavelength?
Okay. PL spectra, as I said before, the PL is the electronic excitation. Okay. So electronic excitation and Raman gives the vibrational excitation. So energy wise, both are different. But the scattering cross section of PL is much higher than the Raman. So if you use the same for same laser excitation, the PL will be much stronger than the Raman. So that's the stronger intensity in Raman. Okay.
Okay.
Thank you, sir. I can see there are many questions, but you may email to Professor Singer about this. So thank you, sir, for delivering such an excellent talk. I would also like to thank Utpal sir because he was moving the slides due to the technical difficulties. So Professor Achinda Singer, sir, we are really lucky to have you in this webinar series. Thank you so much.
Thank you. I'm also very thankful to you. Okay.
So the
Can I make one comment?
yes.
Yeah, those who will get answer for their questions due to time limitation, please note down the email ID of Professor Achinta Singh. It is achinta at the end of acbooks.ac.in or achinto1977 at the end of gmail.com. It is also visible on the screen. You see the blue color. These two email ID, either of these two, you can use to send your question directly to Dr. Washington Sinha to get answer from your question. Thank you.
Thank you, sir. So the next lecture of SEMP 2020 will be delivered by Dr. Sanjay Kumar Mahata.
Yeah, thanks.
Welcome, sir.
Should I share the
So,
content?
Dr. Yes, sir, you may. Dr. Sanjay Kumar Mahata did his master's from the University of Burdwan in the year 2000. In physics in the year 2013 from Saha Institute of Nuclear Physics. He was an ICTP Elettra Synchrotron Trieste, Italy from 2013 to 2014. He was a postdoctoral researcher at ISM CNR Trieste, Italy from 2014 to 2016. He did another postdoc from Aarhus University, Denmark between 2014 to 2018. And now he is a scientist at Deutsche Elektronen Synchrotron, DESY, Hamburg, Germany. He is also a member of German Physical Society. His research interest includes study of the electronic structure and ultrafast dynamics of new paradigm quantum materials, example Dirac materials, well semi-metals, transition metal dichalcogenide, proton and free electron laser-based angle, spin, time-resolved photoemission spectroscopy. He is also interested in strong correlation and collective ground states, example charge density waves, etc., in low-dimensional systems, and how factors such as quantum confinement and reduction of symmetry affect those states. He's also working on some other complementary techniques such as scanning tunneling microscopy, X-ray photoelectron absorption, etc., to understand the structure and magnetic properties of the materials. His quality of research is manifested through his publications in high-impact journals like Physical Review Materials, Physical Review B, SES Nano, etc. So today he is going to give a presentation on does a Dirac cone exist in mono and multilayer silicon on AG1, please.
Okay, thanks a lot, Debolina, for the kind introduction. And I also thank the organizer for inviting me for this seminar. And special thanks goes to Professor Utpal Sarkar for inviting me. So I also must thank the previous speaker for a nice introduction on the Raman spectroscopy, which is basically on the to measure the vibronic. It's a kind of vibronic spectroscopy, and what I'm going to talk about is basically electronic spectroscopy. Or I'll discuss about the electronic structure of two-dimensional materials. And all we know, the two-dimensional material, the greatest example is graphene. So graphene is nothing but hexagonal honeycomb network of carbon atoms, which one can peel off from graphite. And this material shows exciting electronic properties near the Fermi level with characteristic Dirac cone with linear dispersion. And the rest mass of of the electron at the Dirac point is 0. And after the discovery of graphene, there have been a huge interest in other two-dimensional materials. And I'm going to talk about one of its cousin material, which is silicene, which is basically when you replace carbon with silicon. So it's a hexagonal honeycomb network of silicon atoms. And also multi-layer silicene, which is basically many layers of silicene. And then our question would be, or our main intention would be to see if they host any kind of Dirac cone in the electronic structure. And the silicene, so far there have been no report of freestanding silicene. So we have to grow silicene on top of some substrate, and in our case it would be silver 111 with on which it doesn't react much. If you put on other transition metal elemental surface, it reacts more than on silver 111. Okay, so so our question would be to see if this kind of Dirac cone exists on silicene or on multilayer silicene. And I must acknowledge all the people involved in this project. So this is the work done when I was in Italy, in Trieste, and in the group of Professor Carlo Carboni. And these are the people who are involved who are involved, and Valerio Bellini, he did the DFT calculations. And these people are from Elettra, who also contributed in doing the experiment, and Professor Carsten Horn from Berlin, who also contributed in the project. So the outline of my talk would be the following. So first I will talk about the experimental techniques, which are angle resolved photo emission spectroscopy. So it's called ARPES, and low energy electron diffraction, which is LEAD. So basically, angle resolved photo emission spectroscopy is a technique which will be employed to study the electronic band structure of the solid surfaces, and LEAD will be used to study the structural property of the surfaces. And then I will give a brief introduction on silicene, what are the standing problems and what are the things we can expect. And then I will move to two different topics. One is silicene on silver, and we would like to ask if single phase silicene exists, and if so, or if not, if there are any direct cone. And then at the end, I will discuss about multilayer silicene with the same question, does it exist? Okay, so let me start with the experimental techniques we use to study these things. So angle resolved photoemission spectroscopy we use to study the electronic band structure of these materials near the Fermi level or the valence band electronic structure. And this technique is based on photoemission spectroscopy. So in photoemission, all we know, when we shine a material with sufficiently energetic photon, the electron will come out from the solid surface. And by analyzing the kinetic energy of the emitted electron by using this kind of hemispherical state-of-the-art analyzer and using the energy conservation equation, we'll be able to find out the binding energy of the electron inside the solid. So we measure electron kinetic energy. H nu is the photon energy, which we know, and phi is the work function. So it's a very simple equation, and we can easily extract the binding energy of the electron inside the solid. And using this kind of state-of-the-art detector, one can also map the emission angle of the electrons with respect to the surface normal. Here you can see this in this detector, the different electron emitted with different emission angle are mapped onto different part of the detectors. So in this way, the different emission angle, which is theta, can be converted into K parallel, which is basically the momentum of the wave vector of the electron. So in a single shot, what we get is basically kinetic energy versus emission angle. And then, as I said, by using this equation, the whole spectra or whole image can be converted into binding energy versus K parallel. And this is nothing but the band structure of that solid surface, which is energy versus momentum. So in a single shot, what we get is band structure of that solid surface along a particular symmetry direction. And then what this light source can be different thing. Like in lab, it could be a discharge lamp, which could be helium or xenon discharge lamp, or laser sources, or it could be synchrotron. And it could also be free electron laser. And the intensity of this light goes top to down. And depending on one's choice or on the experiment, one can choose one or the other. Okay, so the data acquisition basically works in the following way. So here you can see a schematic of the analyzer, and this is the sample, okay? And then in a single shot, as I said, what we get is energy versus Kx. So this Y is energy, and this is Kx, along a particular symmetry direction. Let's say we have a 4-fold symmetry system with a or 2-fold symmetry system, and we are let's say acquiring the data along gamma 2x. And then by rotating the sample, we can acquire different slices, and we can make this sliced 3-dimensional data stack. And then by symmetrizing the whole data set, we can make make a three-dimensional data set or a data log. This data can be cut in different energy to see how the constant energy look like. Or we can also cut at different kx or ky to see the topology of the band, how it is changing along orthogonal directions. Okay, so this is what we do in angle resolved photoemission spectroscopy. Good. So now let me tell you something about low energy electron diffraction. So it is a technique where we shine the material surface with a monoenergetic electron beam. And then the backscattered electrons are collected on a fluorescent screen, okay? And by seeing the spot profile or the spot symmetry of the spots, we can try to understand what is the structure of the material and how clean the surface is. For example, let's say if we start with silver 111, on which we have grown silicene, it has a hexagonal symmetry. And if we shine this material with the electron beam, we will see a diffraction spot on the fluorescent screen like this. So it will have 6 spots, basically with a hexagonal symmetry. And from this, we can construct the Brillouin zone, right, which will also be hexagonal. And then we can also know what are the symmetry directions are. Like this is gamma to M, this is gamma to K. And then if we put something on top, for example, let's say if we put silicon, which are basically these, and here you can see this also has a hexagonal structure with a bigger lattice parameter, okay, this red one. So in diffraction, in the K space, what we would expect is basically a smaller hexagon. So this is what you would see if you delete. So this will be the spot coming from silicene. And then if we and then we can also construct the Brillouin zone of that silicene surface. And we can have a different structure of silicene on top of the surface, which is probably rotated by few degrees. You can see it's the same structure, but rotated with respect to the silver 110 axis. And then if we shine electron beam on both the structures, then you would see some extra spots in the lid in low energy electron diffraction. So here you can see if you zoom in, so there is one spot from silicene and there are 2 different spots coming from this structure, because this structure can be rotated clockwise or anti-clockwise, and there will be equal distribution of those two rotated domains. And this is what we would get. Okay. Now let me give you a brief introduction. So as I said, silicene is a cousin material of graphene. So it's basically a hexagonal honeycomb network of silicon atoms. And here we expect some nice properties, like this. We want to see a honeycomb atomic structure, and an electronic structure or band structure near the Fermi levels should host Dirac like features. And this makes this material really interesting. But the experimental realization of all these are really challenging, because we have to synthesize silicene on top of some substrate, and then there will be some kind of structure which we need to examine, and then there might be some effect from the substrate. I mean, the substrate electron can hybridize with the silicene electrons and can somehow distort the electronic properties of the silicene. So that's why matching between expected and observed properties would be quite a challenge. So let me tell you that this carbon, so why silicene is kind of why we are expecting that there will be silicene. Is it naturally possible or not? So in carbon there are 3 different kind of hybridization of the carbon atoms: sp3, sp2, and sp. So sp3 gives you diamond structure, sp2 gives the graphite structure, and sp gives acetylene structure. But in silicon, it is mostly only diamond-shaped silicon with sp3 hybridized silicon atoms. And we need to really see if this sp2 hybridized silicene or silicon is possible or not. Because if you see the energy difference of the 2s and 2p of carbon atoms, it is 8.7 electron volt in the case of carbon, whereas in silicene it is 7.2 electron volt. So the energy difference is not that much, and there might be significant overlap of s and p orbitals, and maybe the sp2 hybridization is not really possible. So these are a cartoon of this sp2 and sp3 hybridizations in carbon and in silicon. So in carbon, if you see, the sp2 hybridized electronic structure or electron configuration is the most stable state, and the diamond or sp3 hybridized one is a metastable state. Okay, so that's why we get a lot of graphite in nature than diamond. But in case of silicon, it's the opposite. So sp3 hybridized configuration is the most stable one, whereas sp2 hybridized is a metastable state. So in that means that even if sp2 hybridized silicon exists, we need to prepare it in a very special condition. And this will be metastable in nature. And metastable in nature means if there is any kind of excitation available, the whole structure will melt or will transform into sp3 structured silicon. So there are some theoretical calculations from 2009, and they calculated that okay, this will be because of this metastable state, there will be buckling of the honeycomb phase. Okay, and there can be two different like these low buckled structures are really metastable with respect to structure, and this lowest possible buckling which was achieved was 0.44 angstrom with mixed sp2 and sp3 hybridization. Okay, and what should we expect in the electronic structure? So this is the silicene band structure with planar silicene. So all the silicon atoms are on the same plane, and this is low buckled silicene. That means like one silicon atom is at a different height with respect to another, with 0.44 angstrom higher than the other one. And then if you see their electronic band structure, if you compare them, and you can see that the band structure is nearly same. There are no big difference, except there is a gap opening like here. And this is because of S and P mixing, because of some sp3 hybridized bands. But most importantly, the Dirac cone is intact. Okay, so even if we get a low buckled silicene structure, we should expect to see some kind of Dirac cone, because there is no change in the Dirac cone, even if it has a status. And these are the lattice parameters of silicene and graphene. With pi bandwidth in graphene, in silicene would be around 3 eV. So this is the pi bandwidth. So you see the bottom of the pi band is around 3 electron volt. In case of graphene, it will be at -10. And the Fermi velocity of the band crossing the Fermi level, these bands, in case of graphene, it is 1 × 10⁶ meter per second. But in case of silicene, we expect to get something around 0.5 × 10⁶ meter per second. Okay. So let's see if this silicene on silver, can we achieve this single phase structure? And if so, do we see any kind of Dirac cone? So this silicene was sized on different substrate, like on silver 111, silicon on silver 111, on zirconium diboride, and on iridium. But if you see the literature, most of the studies are on silver 111, and this has a special reason. And if you compare the lattice parameters of silicon and silver, they are exactly 4:3. Okay, that means if you grow silicon on top of silver, then every fourth atom of silicon would match with every fifth atom of silver. And that's why you would get this kind of structure. So if you follow this, from here to here, you can see there are four silver atoms which are in gray. So 1, 2, 3, 4. But along this direction, if you count the silicon atoms, there will be only 3. So, and this is the reason it will give you a 3 by 3 or 4 by 4, depending on what is your reference structure. We will get 3 by 3 or 4 by 4 structure of silicene. And the lead pattern, because of this 4:3 lattice ratio, you would expect to see this kind of spots, which are called 4 by 4 spot with respect to silver 111. And from this, by seeing this spot, one would be able to understand if we have the right phase of silicene or not. Okay. And sorry, in this paper, this was a PRL in 2012, this group claimed that they could achieve this single phase silicene with silicene 4 by 4 structure. But then we studied the same system using the same kind of growth recipes, and what we found that this is probably not true. And let's try to understand what exactly we mean by different structures. So this is a 4 by 4 structure. This is a simulated structure, silicene on top of silver 111, and this will be the simulated lead pattern. So we would expect this kind of spots. Okay, these black circle ones are the spots coming from silver, and these are the spots from silicene. So what we would expect is basically this, which we will call 4 by 4 spot. Okay, but then the silver networks, or sorry, silicene networks can be rotated by 13.9 degree, and structure will be called root 13 by root 13 rotated by 13.9 degree with respect to the silver 110 axis. And in this case, the simulated lead pattern gives you this kind of spots, and these are root 13 by root 13 spots. Okay, and then it has another structure which is called 2 root 3 by 2 root 3. Okay, and in this case, these two spots are a bit far apart if you compare with root 13 by root 13. So in root 13 by root 13, they are very close to each other. In root 2 root 3 by 2 root 3, they are far apart. And what we did this growth of silicon at different temperature, and we tracked the intensity of these spots in the lead pattern as a function of coverage. Okay, so this you can see, these are a different monolayer. Okay, monolayer means when it is covering the whole surface of silver, and they are grown at different temperature, 296, 280, 268, and 218. Let's try to concentrate along at one monolayer at different temperature. So what you can see at lower temperature, 218, we see a very strong intensity from 4 by 4, and there are some signature of root 13 by root 13, right? And then as you increase the temperature, you see these spots are going away from the main 4 by 4, and here they are far, they are really far apart from each other. So this phase is 2 root 3 by 2 root 3. This is some kind of mixed 2 root 3 by 2 root 3 and root 13 by root 13, and this one is 4 by 4 plus root 13 by root 13. Okay, and if you really track the intensity of different spots, like in black, I will show you the intensity of the 4 by 4. In red, I will show you the intensity of root 13 by root 13. And this spot is coming from silver, and the other one is coming from other domains. And if you see this will give you this kind of profile. And at exactly one monolayer, if you see, we have several different domains, contribution from contribution from yellow, green, red, and black. That means even at lower temperature, we cannot achieve only 4 by 4. Okay, there is a little contribution there is a contribution from this root 13 by root 13 also. Okay, so that means the single phase silicene on top of silver 111 doesn't exist. So different structure will always coexist in various proportion, and that would really depend on the coverage and on the growth temperature. Okay, so what one can really do, one can try to minimize the contribution of root 13 by root 13 by playing with the temperature, the growth temperature, and this is what we did. We grew a film with 4 by 4 and very little contribution from root 13 by root. Okay, now let's see the electronic structure. So if you see the theoretical band structure of silicene, it has a very simple band diagram, you can see. So it has basically 3 bands near the Fermi level, 1 pi band shown in orange color, which is crossing the Fermi level at K point, and then 3 sigma bands shown in green, sigma 1, sigma 2, and this is sigma 3. And if you see the band structure of silver, it has this kind of structure, like below 3 electron volt binding energy, there are strong D bands, and then there are the sp band crossing the Fermi level. So this gray plot is basically projected bands of silver 111. And then we also have a surface state at gamma, okay, this red one. Okay, now if you do the experiment on silver 111, this is what we get. So this is the experimental band structure from angle resolved photoemission spectroscopy. So you see this is the surface state, and these are the projected bands, projected silver sp bands. Okay, and then if you put silicon on top, this is what we get. Okay, after putting silicon, we can see there are many different bands. Like this parabolic band, one can compare with the silicon sigma band, like this band. Okay, and then there are silver sp bands visible, like we saw before. But in addition, we also see some parabolic bands, like this one and these ones, and they are silicon sigma bands. So they are basically these bands which we see here. But in this spectrum, we don't see any signature of pi band. We don't see any band which is crossing the Fermi level with this kind of dispersion. Okay, so now the question is, does silicene preserves its electronics on silver? And it's the same paper again, it's PRL in 2012, and they claimed they could grow single phase silicene. And they also claimed that they saw a compelling evidence of direct cone coming from silicene. So you see, they have shown the silver spectra near the K point of silicon. There are no band, and after putting silicon, they could see a linearly dispersing band up to 0.3 electron volt. And then they claimed that this must be the silicene direct cone at the K point. And then in another paper, they claim that, and at the M point of the silver, which is basically this one, M point of silver, which is also equivalent of the K point of silicon, they could also see another parabolic band, which they also claimed that it's a silicene direct cone. But and the bandwidth was larger than 3 eV, and they claimed the velocity, the Fermi velocity of this band is 1.3 10 to the power 6 meter per second, which is even higher than that of graphene. But few other groups did the same experiment using scanning tunneling spectroscopy. They could not find any signature of linear band in silicene. They couldn't find any signature of direct cone, and there was also no clear pi band in DFT calculations. Okay, so there are no clear band. There are a lot of foldings because of this 4 by 4 or root 13 structure, but there are no clear indication that there is a direct cone coming from silicene. And this from this point we took we decided to do the experiment on silver 111. We grew the same film And we did the similar kind of experiment using the same photon energies and similar conditions. And what we found, so these are the band structure reported in this PRL. And what we did the same experiment on silver, and we found this silver band in the both side of the detectors, which was not reported in this PRL paper. So there must be something wrong. And after putting silicon, what we found that on the left and the right side of the detector, we could always see this kind of linear bands crossing the Fermi level, and they are nothing but silver band. So this is just the silver band what we are seeing here after putting silicon. And that should not be a silicene band. So here you can see that after this is silver 111 and this is after putting silicene, we could see the same silver band crossing the Fermi level, and it is not related to any silicene band structure. So basically there is no new band at the K point of silicon. So the claim they did in PRL is kind of wrong. Now let's see what happens at the M point of the silver. These are the M symmetry point of the silver. Okay, and here you could see that after putting silicon, we also see this kind of parabolic bands. Okay, what they claimed is coming from silicon. Okay, and we see this kind of band, and let's assign this band as I. Okay, and in the following I will explain you what this I band is. Okay. So if you see the topology of the band, so what we did, we probed the band along this direction, along the red direction shown here, and along the blue line direction, which is the orthogonal direction along this. So let's say if you have a cone, what would happen? If you have a cone, then doesn't matter in what direction you cut it, like along this direction or along this direction, you would always see a parabola. Okay, you would always see a parabola. In our case, we see parabolas in both cases, but in this case, we see maxima this direction and minima along this direction. And this can't be a cone. Okay, if it was a cone, we would also expect a parabola like this. Okay, so what we claim that this is a saddle-like band structure. Okay, so it's a kind of a saddle, like a horse saddle. So it has a minima along one direction, and the same point is a maxima along the orthogonal direction. So it's a saddle. Okay, so this is not a cone, and this is not a direct cone. And the same thing you can understand from the constant energy cuts. So in constant energy cuts, what you expect, like if you have a cone and if you cut them in constant energies, you would always see circles. Okay, but what we saw here in silver and after putting silicon, we always see this kind of dog bone like structures, not circles. So there is no evidence of direct cone sections. And from here, we said that, okay, there is no experimental evidence of direct cone, but then we must understand what this I band is. And to do that, we did some DFT calculation. And these are the calculations of silicon on top of silver 111 in a folded Brillouin zone. And you some green bands. These are coming from silicon sigma orbitals, okay? And these orange ones are coming from silicon pi orbitals, okay, or silicene pi orbitals. And these are projected on the silver 111, and you can see these are silver contribution. So if you say that there is a pi contribution in the band structure, then you can definitely say that these contributions are somehow set by this silver 111 band structure. Okay, so from here we can say that the sigma state, they are not really affected by the substrate because there are no silver states here. Okay, but for the pi state, they are strongly affected by the silver 111 because they also lie in the same energy or they have the same kind of dispersion. And what we claim is these pi states lose their two-dimensional character and fade out when we put them on top of silver 111. And this you can easily understand. The silver has a very simple band structure, like this has a parabolic band like this. And if you fold them into 4 by 4 Brillouin zone, this is what you will get. Okay, this one. And if you compare this one, this band is basically this one. Okay, and this flat band is basically this one. Okay, so it is basically nothing but coming from silver 111. This is basically silicon induced interface state. So you get this when you put silicon on top of silver 111, but the orbital contribution of this band says that it is coming only from silver 111, or most of it is coming from silver 111. And we did the same thing on 2 root 3 by 2 root 3 structured silicon, which was grown at different temperature at 270 degrees centigrade. And we saw the similar kind of thing. There was no Dirac cone at K point of the silicon, and there was also no Dirac cone at the M point of the silicon. It's the same thing. You see a parabola with a maxima along this direction and with a minima along this direction in the orthogonal direction. And so there is no Dirac cone at the M point also. So from here we said that silicene, we had some kind of, like on freestanding silicene, we expect similar properties as graphene, but it is very unlikely to be produced. So then we did supported silicene, which has honeycomb buccal structure, which is okay, but there's a strong interaction with the metal surface, strong hybridization with silver 111. And there is no Dirac band. So from here, we can say that silicon on silver 111 does not show at all the electronic structure of silicene. There is no Dirac cone. And at the same time, one can say that, okay, let's grow this on some other transition metals, but silicon reacts with other metals, so that won't be a good choice. So what we have to do is we have to grow silicon on some inert material, and one has to find a suitable candidate where it doesn't hybridize with the structured bands. Okay, so now let me tell you something about multilayer silicene, and the question would be, does it exist? Because in 2013, by a group who published PRL on silicene, they published another paper in APL claiming that multi-layer silicene exists with a Dirac cone. Okay, so these are the multi-layer silicene structure with root 3 by root 3 rotated by 30 degree. And then you can see that they see some kind of Dirac cone at gamma, okay, with the unoccupied part and the occupied part. So these are the pi bands and these are the pi star. And then they say that this multi-layer silicene might offer standalone silicene. And this paper was published, and there was another one also. But then soon after, the same group claimed that this structure has an interlayer distance of 2.35 angstrom. This has a sp2 layered structure, so it is basically multi-layer silicene, like multi-layer graphene or graphite, and it has this sp2 kind of hybridization. But from the STM, from the topograph, what they found that the jump of single sorry, I can't see this. This jump of this single silicene layer is around 3 angstrom, but ideally it should be 2.35 angstrom, what they didn't find. And then this Japanese group did the same experiment, but on two different kind of systems. So they did lead experiment, low energy electron diffraction, and what they did, they chose one of the point and tried to see how it changes with the incident energy of the electron. And this is called lead IV. I is basically intensity, and V is the voltage. Voltage is basically the energy of the electron. These are lead IV characteristics of two different systems. One is multi-layer silicene, prepared in the same way the other group claimed. And the other structure is basically, it is silicon 3 by 3 structure on top of it is root 3 by root 3 silver structure on top of silicon. So as I said, multilayer silicene has a root 3 by root 3 structure. So this one is silicon on top of silver, and this one is silver on top of silicon. So these are two different systems, but pretty similar. So here they had put silver on top of silicon and silicon on top of silver. And if you follow the lead IV curves, they were quite similar. Okay, and then they claimed that okay, this multi-layer silicene structure is pretty close to that of silicon on silver. And then at the same time, they said, okay, maybe this multi-layer silicene can be synthesized in a very small, very small temperature window, because they could not explain star band, what they claim near the Fermi level. They could not fit with a parabola, they couldn't fit with a linear, and then they said, okay, maybe there is a signature of multi-layer silicon which can be only synthesized in a very narrow temperature window. A similar kind of experiment was done by another American group and was published in STS Nano. And they did the same thing, silicon on silver and silver on silicon. And they did STM, and what they found, the structure looked exactly same. So if you follow these structures and these structures, they look exactly same. It is just little bit focused or defocused. And also the interlayer spacings and interlayer spacing and also the lattice parameters are very similar. And from here, they say that they have indistinguishable structure from silver on silicon on the reverse structure, and the interlayer spacings are identical. And this, of course, could not they didn't give any kind of conclusive evidence like what multilayer silicene is. And then what we did, we decided to do this experiment, and what we did, we grew a wedge. So basically multi-layer silicene with a different wedge structure on silver 111 and at a particular temperature. And then we acquired photoemission from the silver 3D core level and silicon 2p core level as a function of thickness at different points. And then you can see that these are changing slowly, okay, as we are putting more and more silicon, the intensity of silver is dropping, whereas as we put more and more silicon, the intensity of silicon is going up, and also the shape is changing. And then we did this at different temperature, and then what we did, we plotted, we tracked the area under this curve of silver, because we are putting silver on silicon. Sorry, we are putting silicon on silver, so the silver intensity should drop exponentially. And this is what we expected. So you see, at different temperature, we plotted the intensity of silver, and they are not dropping exponentially. This is the exponential curve, the blue one. And none of them are dropping exponentially. The green one is changing its slope, so it is basically not decreasing but increasing, and it is at very high temperature, 270. And from here one can say that at this temperature, it is the silicon film is breaking and making some pillars, so that it has some open areas of silver 111. That's why we see more and more silver here. But
Sir,
at lower temperature, yeah.
Sir, another 5 or 7 minutes you may take, sir.
Yeah, so I'll finish in that time. Yeah, sure. Thanks. So none of them is matching with the exponential curve. And from here, we said that, okay, there could be only two scenarios there could be only two scenarios. Either silver is coming on top, or we are not growing a waiting layer of silicon. And from there, we did some simple decomposition approach, and what we found that there is another component of silver which is growing up even at the lower temperature. And this component is basically coming from silver on top of silicon. Okay, so this is the very thick film of silicon grown on silver 111, and if we do photoemission on this point on the wedge, then you can see there are two components. Okay, so and on this this blue curve is totally shifted from this black curve. And this silver is basically silver on top of silicon. So what is happening when we are growing them, the silver is going on top of the silver, on top of the silicon. And then we did this angle-resolved photoemission spectroscopy of these structures grown at different temperature, and we can see that these structures, valence band structure, are like this. And at 270, we see clear indication from silver. These are the silver bands, but at lower temperature, there are no silver bands. So this growth can be compared. And then we also grew this √3 by √3 silver on top of silicon, the reverse system. Then one can see that the band structure is pretty similar. They are both same. And from here, we said that, okay, this is basically the same system. So there must be some silver which are going on top of silicon when we are growing at 200 degrees centigrade. And even if you compare this band structure at different temperature, every band one can compare with the reverse system with √3 by √111. And from here, at gamma, you see a surface state, which basically you can compare from here, from this theoretical calculation. This is S1 band is this one, this is S2, and these are S3. And this calculation was done on √3 by √3 silicon, silver on silicon, the reverse system. And from here, we can say that we could not also match the effective mass. And so at the end, what we wrote that the surface state is basically developing into a kind of an interface state due to p-doping of the adjacent p-doping of silver by the adjacent silicon atoms. So from here, what we can say is basically that the bands previously attributed to pi star band, which were claimed to be coming from multilayer silicines, are derived from silver on silicon. Okay, and there is also a silicon modified silver 111 interface state. And the electronic and atomic structure of silicon film of few monolayer or the multilayer silicene looks like sp3 hybridized diamond film of silicon rather than multilayer silicene. So from here, one can say that looks like a dark, swims like a dark, and quacks like a dark, then it is probably a dark. So basically, the atomic structure looks like sp3 hybridized silicon. Electronic structure looks like sp3 hybridized silicon. So basically, this multilayer silicene is nothing but sp3 hybridized silicon. And with this, I would like to thank all of you for your kind attention.
Thank you so much, sir, for such wonderful presentation. Now it is open for discussion. You may please raise your hand or put it in the chat box. One question is there in the chat box, sir, by Rumal Singh. What information give the silicyl Dirac cone physically? I guess. Hello, Rumal Singh,
Sorry.
you may unmute.
Yeah,
you may
I don't
unmute
see
yourself.
the comment.
Okay, sir, I am telling you. Hello, Rumal Singh, you may unmute yourself and put the question directly.
Hello, Rumal. Hello.
No problem. You can tell me the question.
What question is asking? I could not get actually. He's writing that what information give the silicyl Dirac cone physically? It's like it is like that.
Okay, what information give the silicene Dirac physically? Okay, so physically, it is basically if you get some kind of Dirac cone in a material, that means the electrons are moving very, very fast near the Fermi level. They are almost massless. Okay, the Fermi velocity would be very, very high, like in graphene. And that will be really, really important for the electronic devices if someone want to make out of it. Yeah.
So anybody having any other questions? Or you may directly email to Sir Mahata. Or you may put it in the chat box also. no more question. Okay,
Okay,
another question.
no problem. Thanks. Yeah.
Sir, questions are coming. Sir,
What is the lowest thickness of silicon layer? Yeah, the lowest thickness would be one layer, just one atom of silicon. Yeah, now it depends what you can also say it half a monolayer, but in that case, half of the surface is covered and half is not. But the lowest thickness you get is single atom of silicons. So it's one layer.
another question is, what is the recent application of this topic?
There are no recent application of this topic. Actually, after this paper in PRL, people were saying that, sorry. So people were claiming that this silicene can replace the silicon industry. Okay, in a way, because all the devices, all the transistors and everything are made of silicon, right? And if you somehow replace this with silicene, then there might be very fast devices, which will be also light in weight and also faster. But I think they were wrong because they were assigning bands to silicene, and actually they are not. They are coming from the substrate. So I think one cannot immediately have any kind of application from the silicene or multilayer silicene. They don't really show any kind of exciting properties, I would say. One need to
Sir,
grow them on some other substrate.
okay.
Yeah.
So another question from Sukhvinder.
Yeah.
What is the surface area of silicon? I guess he's asking.
Surface area? What does
Of
this mean?
silicon.
I am unmuting.
Yeah, please. Yeah.
Hello, hello, Surinder. Hello,
Yes.
hello, Surinder.
Hello.
Hello.
I want
I
to
can
ask
hear
a
you.
question. What is surface to volume ratio actually of silicon?
Surface to volume ratio.
Yes.
Oh, this one need
It's
to
high or
calculate.
low as compared to other 2D materials?
Yes.
It's high or low compared to other 2D materials?
No, I haven't calculated it, so I cannot give you any number. But I can give you the lattice parameters, and lattice parameters were given in one of the slide. I you the silicon has this one, so it's 3
So, Govinda, just
so
to
3.87 angstrom.
Okay.
You can calculate the area and the volume. I'm not sure because there are no 3D counterpart, I would say.
Okay. Thank
I
you.
mean, there are no sp-ized silicon structure. They are all sp3.
Sanjay.
Yeah.
Yeah. Just in connection with the previous question, recent application of this topic, you may highlight what structural information you can get from the APRS and the use of Raman Spectroscopy and heat experiment. You have only highlighted
Could you
the
please
answers.
increase your volume? I mean, I can't hear you very clearly.
Are you hearing me properly?
Yeah, but it's
Voice is low,
not very
sir.
clear.
Voice is low. Okay, I'm writing.
Okay.
I'm
Yeah.
writing the.
But now you can tell me. Maybe it's better, little better than
Okay.
before.
Okay. So application of APRS and heat, that you can also highlight. Only in silicon structure, we have highlighted the application of silicon structure. You have also talked about APRS and the use of automated spectroscopy techniques and the rate. So the two techniques you can just read some more words that how you can use these APRS and need to get the information about the structure of the machine.
Okay, so if I understood well, your voice was not very clear. What I understood that what are the information, what are the structural information one can get from angle resolved photo emission and lead? Am I right?
Yes, yes.
Yeah. So basically, as I said, both the techniques, or maybe I didn't mention, so both the techniques are very surface sensitive. Okay. So you are getting information from the top layer of the surfaces. There must be from 5 to 10 angstrom. So one cannot say much about the bulk structure, but the surface structure, yes. So if you see a lead pattern, like from the symmetry of the lead pattern, one can say what kind of lattice symmetry it has, what kind of surface lattice symmetry it has. Like here you see a hexagonal symmetry, so you can say that my surface must be hexagonal. And from the spot profile analysis, that means by seeing the spot intensity with respect to background and everything, one can also say that, okay, if you have any dirt on top or not, if your surface is well ordered or not, okay, if you have any kind of surface, like if you have any how to say, any kind of stepped surface or anything, your lead pattern will be little bit different. Okay. And also, like when you are putting something on top, as I showed, you are getting another lead spot. And from there, you can calculate the lattice parameter of the overlayer with respect to your substrate. So these are the quantitative analysis one can do. But the error bar will be little higher than other techniques. So if you really want to determine the structural parameters, then I would do X-ray diffraction. Okay, not lead. The lead is just to know if my surface is good, if I have what I wanted to have on the surface, and also to align the sample along a particular symmetry direction.
Oh, thank you.
Thank you, sir. Thank you so much, sir, for this
Welcome.
excellent delivering this excellent talk, and we are really very
Okay,
lucky enough to have you in this webinar series.
thank you.
So
Maybe I
questions,
can
there are
stop
many
sharing.
questions. You may please email to Sir Mahata. Due to the shortage of time, we can't take many questions. So with this, we have come to the end of today's event, ACMP 2020. Now, I would like to have some feedback from some participants about the webinar, how they felt about it. So, experience, you may unmute yourself and share your experience. Hello. I'm requesting from the participants, you may share your experience.
Participants are requested to share your experiences.
Okay, I'm Sujit Tiwari from Karimganj College. So, am I audible?
Yes,
Yes,
you
sir.
are.
Yes, sir.
So, at the outset, I like to congratulate our Department of Physics, Assam University, all the faculty members, Utpal Sarkar sir, for organizing such a nice webinar. Where what I found is that in this critical juncture, where entire our human race in this world are facing, we have made such a nice use of this opportunity that most of the resource persons I found, their deliberations were so lucid that even the graduate students, starting from UG students to PhD research scholars, all have been definitely benefited. Not to name one particularly, but all the resource persons were really their deliberations were very good, and I am hopeful that definitely these deliberations have made many of the research scholars to undertake research in the fields that have been the works that have been discussed here. So once again, I thank our Department of Physics, all the resource persons, all the students and research scholars involved with this, and definitely it's a great one, and we like that such things will definitely be arranged once again and also in future. Thank you.
Thank you, sir. Thank you. So, anyone else from the participants? Many of them are putting it in the comment box. So, you may unmute yourself and say something.
Hello.
Hello. Yes, yes, you are audible.
Yes, I am Ridupana Mandal. I am a research scholar of Jadavpur University. Okay. I really enjoyed this webinar. All the topics are very helpful and informative. Learned so many things. Thanks to all the resource persons for their enriched presentation. And last, thank you the organizers for organizing such a beautiful webinar. Thank you very much.
Thank you, Rituparna. Some more we can take. Anyone else? You want to share? Everybody is writing. They're putting it in the chat box. Okay. So, from the participants, anyone else? You want to say something?
Debolina, you can say from the chat box also. You can read some of them.
Okay, okay. Okay, so Nikhil Parasar is saying that it was a great experience. Thank you for giving me this opportunity to attend the webinar. From then Algama Masood. Many of them are telling. Okay, I'm reading it out. Thank you very much for organizing such a wonderful webinar in worldwide pandemic situation. Thank you, Utpal sir and your team and Department of Physics at University. Deepak Majumdar is also telling that the webinar was well organized and presents very interesting talks. Talks consisting of the 4 different areas of condensed matter physics. So it was very beneficial for him. He is writing. Okay. Neeraj Kumar Mishra is also thanking the organizers. Anu Rajendran, he is also writing that the webinar was well organized and presents very interesting talks. He personally loved the photo, and I think rest of them will put it in the feedback form. I must say that the link of the feedback form is there in the email ID of all of yours. So you may put it there, and I think it is activated after 1:30 p.m. It is getting activated, so it is activated. Everybody, please fill up the feedback form. The link is provided in your email ID. More chats are coming. Okay, so
Can you
yes,
ask Madam?
yes, sir. You are not audible properly, sir.
Can you ask Madam to say something?
Okay, I think Sukhvinder is going to say something. Yes, Sukhvinder.
First of all, thanks for this such kind of opportunities to listen the national and international speakers. Especially Raman's Spectroscopy is my favorite lecture here. And congratulations, Dr. Utpal Sarkar, for the such kind of webinars. And thank you for all speakers. And congratulations, Dr. Utpal Sarkar, especially for such kind of webinars. Hello.
So, yes, yes, you are audible.
Congratulations, Dr. Utpal Sarkar, for such kind of webinars. I hope in futures I will listening such kind of hello.
Yes, yes, Sukhvinder, you are audible.
So
You
thank
carry
you
on.
very much for inviting me for feedbacks. Thanks very much.
Thank you, Sukhvinder. Okay, so from now, anybody else want to say something from the participants? Okay, so there are more from the chat box. Thank you all for joining us and participating in this. Now, may I request the speakers if they are willing to say something or share their experience on this webinar? Manna, Sir Singha, Sir Mahatha. if you are willing to say something on this.
Okay, probably let me start. Am I audible?
Yes,
Yes,
sir, you
sir.
have a figure.
Okay, good. I think first of all, I would like to thank the organizers, especially. So I think it went very well, and I attended all the talks actually. So I also enjoyed personally. And today I was a bit late because I was in another meeting. Then I thought I'm missing something, but the session was bit delayed 30 minutes, so I didn't miss, so to say, in that way. And in the program list, actually, I was replaced by another person, Professor Subhadeep Datto, but he requested me to do the personal issue. So, but I would say I was very much lucky in that aspect. So to share, I think there were quite a good number of questions also from the audience side, and that I could understand at least. I could give some message so that people are interested in asking questions. And of course, Professor Utpal Sarkar, because I think he is the key person. I think who to whom I communicated a lot, that who could be the audience and what kind of masses they're expecting. And so that helped me a lot to prepare the talk so that I could reach to the audience. And overall, it's fantastic, even the organization point of view also. And the time point of view also, how you managed, I think it was you just started on time, and I think there was a little bit internet issue with our vice chancellor sir, I guess, so that's why got delayed. Otherwise everything was really on time and nicely organized. Thank you very much.
Thank you, sir. It was really a pleasure for us to have you. Hello.
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 Hello. Hello.
Sir? Yes, yes, please, sir. Okay.
Okay. So first of all, I am very happy to be a part of this program, which is a part of your this Silver Jubilee celebration of your department of the Department of Physics, Assam University. I sincerely thanks to the organizer for inviting me and giving me the opportunity to be a part of this program. And it is indeed a very nice experience. And this is a new uh, type of this conference, this webinar, and in this COVID situation, but this means time and everything, it was very nicely managed. And most important thing is that a lot of students are participated in this program, and they have asked a lot of questions, and all the speakers I have also listened all the speakers talk, and it is really very good. And actually it is a very successful program, and I wish for much more successful program in the near future of your this Golden Jubilee, Silver Jubilee celebration program. And thank you all.
Thank you, sir. We are really very lucky to have you with us. Sir Mehdi, I think he is going to say something. Yes, sir. Sir Mehdi. Hello, Sir Mehdi.
Okay, I must also thank all the organizers.
Hello.
And also Professor Utpal Sarkar for inviting me to give this seminar. And was all, and I also enjoyed the other talks. I couldn't really attend all four talks, but I think I partially attended, and I really enjoyed. So it was a nice mixture of different topics, and it was very well.
Yes.
So thanks a lot.
So
Hello. Thank you, Mahata sir. He was saying something. Sir Mehdi is also trying to say something.
Oh, yes.
But
Can you hear me?
yes. No.
Okay. I would like to thank all of you, especially Professor Sarka, for organizing such a nice meeting. It was, I think, it was very successful. Unfortunately, I missed the first talk of today, but with respect to the number of questions, I found this webinar very successful from the number of audience. It is clearly seen. I hope this could be a starting point for binational between Iran and India webinars and workshop, hopefully. Thank you very much for inviting me for presenting a talk. Good luck.
Thank you, sir. Thank you so much. Great to have you with us, sir. Sir Mahata was also telling something. So, Sir Mahata, we are really very fortunate to have you with us with such presentations. Thank you.
Sorry, I said something, but probably I was not audible because of the connection.
Okay, you
Am I
please.
now?
Yes, you please. Yes, you are perfectly.
Yeah. So yeah, I thank the organizer, and special thank goes to Professor Utpal Sarkar for inviting me. I really enjoyed the webinar. Unfortunately, I couldn't attend all the talks, but some of them I did, and they were really great. So I hope to see you again in future. And yeah.
So, thank you, sir. Thank you. Thank you. It was really pleasure for us to have you. Thank you, sir. Okay,
Can I
now
say something?
may I request?
Something
Yes,
more?
yes,
Hello, Utpal.
yes, sir.
Yes. Yes, Ashita.
Hello.
Yes.
Yeah.
Tell me.
So we should all of us should give a big thanks to Devlina. Actually, she managed everything, and
Sure.
also Professor Salkar for this entire event. Okay, thank you.
Thank you so much, sir. I'm overwhelmed with this. So thank you so much.
So I should say something as a convener of this program. At first, I must say that we are really happy to organize this webinar on this 25th anniversary of the Department of Physics, Assam University, Silchar. This is our first program on condensed matter physics under the umbrella of these celebrations. In this program, around 200 participants, considering both Cisco WebEx and YouTube participants all over the India took place in the first and second day also. And the number we are expected like this. We could see that these interactive sessions was also very good, with the participants coming up with number of questions to the speakers. Though we couldn't able to take all the questions, but I guess the discussion was very fruitful for the participants. And due to time constraint, actually we couldn't able to take all the questions. I'm sorry for that, but this happens actually in the end. Through this webinar, the participants got to know about the recent experimental research going on over the world and computational techniques, the state of all the RDNT calculations you have seen in the past as well as last lectures. We are also sure that the participants will surely get motivated and enthusiasm to start or continue research on condensed matter physics through these lectures as given by our four eminent speakers. And have a good day and a safe stay to all of you. Thank you.
Thank you, sir. Sir, now may I request Otri ma'am? Ready to say something on this, ma'am?
Hello.
Yes, ma'am.
Yeah. So
Hello.
2 days
Yes.
have passed, like just it has flown off, and it was very nice. Actually, I was listening to all the talks, and I could see that interactions were happening and good interactions, which shows that how successful the program is. And I'm really happy that all the resource persons that whom Utpal approached, they agreed, and they like they have spent their so much of valuable time discussing with the students, and this is the main aim of the webinar. And as Utpal said, this was the first program from the Condensed matter group of the department. So really, I enjoyed the program, and I hope that everyone else has also enjoyed. And I have heard the experts also. I have felt that they have also enjoyed the program. So it's very nice, and we'll be organizing different programs over this year. So now everyone has our YouTube channel address, so you can have a keep an eye on that. You can get flavor of different programs that we are organizing. I invite you all for that, and I think we have come to the fag end. And I congratulate everybody who was associated with the organization. I thank Debolina for moderating the program so well, and everyone else also, and whoever else was associated with the whole thing. I would like to thank you all. No one should feel left out. It's a collective effort of the department, and we could do it finally. So I'm very happy about it. Over to Debolina.
Thank you, ma'am. Thank you. With this, we have come to the end. So I again request all the participants to fill up the feedback form provided in your email ID. Okay. I thank all the participants who has joined from all over India to take part in this webinar. I would also like to take this opportunity to thank all the 4 speakers who were kind enough to join us in this webinar with excellent presentations, and our home team also. I'm sure we all are benefited by this webinar in the 2 days fruitful discussion. Hope that the pandemic we can again go back to normal conferences, seminars, workshops. Till then, let us all stay safe and do join us in our next mentioned here. So, thank you all. With this, I take leave. Thank you.